Okay, so when we say that this is the current relation between the base current and the collector current, one thing is very prominent, that it is going to have a different factor than the base common base configuration, and that is ICEO. Now this ICBO or ICEO is greater than ICBO. That can be established from this equation here itself. Okay, because this component we are calling as ICEO. Okay, and obviously it is greater than ICBO. So ICEO is many times established or described in terms of ICBO and alpha DC also. So ICEO can be shown to be equal to ICBO divided by 1 minus alpha DC. Okay, I'm not going into the derivation of this, it's very simple. I leave it to you. Now, what does this actually mean? ICO is the collector current which flows when emitter base circuit is left open and collector base junction is reverse biased. So in a similar way, I can show it to be like this. So I'm keeping the base open, okay, and I'm applying VCC over here, and the current that flows is ICEO. Okay, that is the reason why we are calling it as ICEO. This O stands for when base is open. Now this is reverse current actually, because collector base junction is reverse bias. So obviously this is the reverse saturation current in this configuration, and it is temperature sensitive. So one very important point, obviously ICEO is temperature sensitive, just like ICBO, but again many times of that. So ICO is a very important component when we talk about common emitter configuration. And as temperature increases, temperature of the junction increases, or ambient temperature increases, what happens? ICEO will also increase. Okay, and this effect is often disastrous when temperature increases above a certain limit, and that is the reason why we have to be careful when we employ devices, transistors, specifically bipolar junction transistors, when larger current is flowing, that is larger collector current is flowing, and temperature also is more. Okay, just remember this point. So thermal stability becomes essential. Now we often neglect this term when we say that temperature is not increasing. If we keep temperature constant, for some reasons, I can write IC as beta DC into IB. Now many times this equation will hold when we are not considering the effect of temperature. But please remember, whenever temperature is to be considered, temperature effect is to be considered, we are supposed to use the other equation. Please remember this. Okay. So let us now have a look at the input characteristics. So we'll start with the input characteristics for common emitter configuration. Guys, am I audible?
सर आपकी स्क्रीन फ्रीज हो गई है.
अरे क्या हो रही है, मुझे समझ में नहीं आ रहा है फ्रीज होने का क्या है इशू. एक मिनट, I'll share it again.
Yes, sir.
Is it visible now?
No,
Is the
sir.
one mode gate visible?
No, sir.
Yes or no?
No, sir.
It is so strange.
Yes, sir. Now it is visible.
Okay. So, as we have already seen earlier, we have two sets of characteristics now, again input and output. So in case of common emitter configuration, what is your input current and what is your input voltage? Base is the base current, IB is the input current, and base emitter voltage is the input voltage. So obviously it will be, the input characteristics will be what? IB versus VBE at constant VCE. Now let me clarify again at this point. Somebody had asked last time, input voltage दिया तो output voltage भी change हो जाएगा and all those kinds of things, right? There may be some kind of confusion here, going way back here. Somebody said that if I am changing the input voltage, output voltage भी change हो जाएगा and all that stuff, right? But what we are doing here is we are biasing the transistor. We are not applying anything. समझ में आ रहा है? We are applying the DC voltage. We are simply biasing the transistor and keeping the bias conditions constant, especially for, in this case it is VCE. We are keeping constant and we are trying to plot the this particular relationship. Is that point clear?
Yes,
Don't
sir.
get confused. So let me just pull the figure from for this common emitter input characteristics. Just a moment. Okay. Are the curves visible to all of you?
Yes, sir.
Sir, your screen is not visible.
कोई बोल रहा है विजिबल है, कोई बोल रहा है नहीं विजिबल है, ये क्या है? तो फाइनली विजिबल दिख रहा है या नहीं दिख रहा है?
नो सर,
Yes,
नहीं
sir.
दिख रहा, नहीं दिख
देखो,
रहा।
नो सर।
यस सर। सर बाकी लोग रिफ्रेश
नो सर, नहीं दिख रहा है।
Okay, let me share this again. Is it visible now?
Yes, sir. Now it is
Yes,
visible.
sir.
Okay, so these are the input characteristics for common emitter configuration. As you can see, this is your IB on the y-axis, and on x-axis you have VBE. Okay, and one peculiar thing that we see over here, it resembles exactly the characteristics of a PN junction diode. isn't it? Yes or no? Guys? Hello? Hello?
Yes, sir.
Yes, sir.
Hey, respond karo bhai. I know this is so horrible. Going for online and all that is simply, you cannot have that feel of having a lecture and all that. But again, we are tied up with so many things. So what do you see from here? Let us put down our observations, right? Okay. Observation number 1. As input to transistor in common emitter configuration is always between base and emitter junction, the characteristics resemble PN forward bias characteristics of the PN junction diode that we have already seen. So it resembles PN junction diode characteristics in forward bias. Okay. Second observation that we have is after cut in voltage, after cut in voltage, IB increases. Okay, rapidly with small increase in VBE. This is another observation that we have. You can see here, after this cut-in voltage of 0.6, 0.7 volts, you can see here, a small increase in VBE will cause a large increase in the base current, IB. Okay. So what can you say about the input resistance, Ri? Just like what we had done for common base. It will be delta VBE divided by delta IE when VCE is constant. This is what we have. So from the figure itself, you will see that what is the value of, comparative value of delta VBE? It is small, whereas value for IB is large. So what can you say about the input resistance? What can you say about the input resistance? This value?
Sir, it will be small.
Yes, so I can say that the dynamic input resistance is small. By the way, why am I calling it as dynamic? Anyone? Why am I calling it as dynamic?
सर पता नहीं.
पता नहीं, वो तो तू पूछना चाहिए ना, ऐसे ही अपने आप आ जाएगा क्या कंसेप्ट ये? Okay.
अभी पूछने ही वाला था.
Okay, so whenever you have resistance, for example, we had done this kind of thing. So whenever we have such a kind of thing, let us say, and if I want to find out, this is IB, this is VBE, the same curve, and if I want to say find out the resistance, I can do that as a static value. So this is this point. If I plot, so this is the value of, let us say, this is your IB1, and this is VBE1. Then my static resistance or DC resistance will be R. DC will be equal to VBE1 by IB1. Whereas if I want to find out the dynamic resistance, what is the change here?
It will be delta VB.
It will be delta VB by delta IE. So that is the meaning of dynamic resistance versus static resistance. Are you getting it now?
Yes, sir.
Okay, observation number 3. For a fixed value of VBE, IB increases. Okay, a fixed value of VBE. IB increases as VCE is decreased. Let us see that. So if I draw a straight line here, for a fixed value of I don't know whether you are able to see that or not. Okay, I'll do it once more.
सर आपकी वॉइस नहीं आ रही है.
Guys, am I audible? There was a call drop here.
Yes, sir.
There was a call drop. Okay, now is it visible? The OneNote page.
Yes, sir.
Yes, sir.
Okay, so why does this phenomenon happen? Is because as larger value of VCE, which results in a large reverse bias at CB junction. So if VCE is more, the reverse bias at collector base junction is more. This will increase the depletion region and reduces the base effective base width, which we have already seen. Hence, there will be lower number of lower recombinations. Okay, and this actually reduces IB. Please remember this phenomenon. Okay, so these are the 3 observations that we have for common emitter input characteristics. Let us go for common emitter output characteristics. So B, output characteristics. Let me pull the curve. So are the characteristics visible to you?
Yes, sir.
So what is it? Basically, which parameter versus which parameter?
Sir, collector current versus VCE.
Yes. So it is IC versus VCE at constant values of.
So IB.
Yes. Very good. So at different values of IB, I'm going to get different curves. All right. Let us start writing our observations here. Okay, observation number 1. Value of beta DC of transistor can be found out. The value of beta DC can be found out at any point So how can you find out value of beta DC? What is beta DC, by the way? We've already seen what is beta DC.
So like for
This equation, consider this equation. So what is the relationship between IC and IB? IC is equal to beta DC into IB, right?
yes, sir.
So if I want to find out beta DC, what should I do? I should simply, from the characteristics, I can simply find out beta DC by taking the ratio of this IB, any value of IB and corresponding value of IC. Okay?
Yes, sir.
So that can be done. All right. So for a fixed value of VCE, how are you going to find that out? See, this is a curve. So how are you going to find out? You're going to first of all fix VCE and then maybe draw a line like this. And then for that value, for that particular VCE, I'm going to find out the value of IC. Okay, for this, and then divide it by IB, which will give me beta DC. All right.
Yes, sir.
Okay, observation 2. From these characteristics, what we see is one more important thing, that for a change in collector emitter voltage, that is delta VCE, causes little change in collector current. So if I see here, if I change VCE, see here, if I change VCE by a larger amount, the collector current change is not that much. It is there, but it is very, very small. Are you able to understand this?
Yes, sir.
So again, what will be the output resistance? By the way, how do you define output resistance? RO? Output quantity divided by output voltage divided by the output voltage. Output voltage divided by the output current. Okay? At constant value of some input current. So here in this term, what we have is delta VCE divided by delta IB, delta IC at constant value of IB. So from this figure, you will see that delta VCE is more, delta IC is small. So what can you say about the output resistance?
Sir, it will be higher.
It will be high. Okay, output resistance is higher. Very important observation. Okay, observation number 3. Again, you can see that this is divided into, this region is divided into 3 or 4, let us say 4 regions. Okay, Again, you have saturation region, you have cutoff region, and you have active region. Also, you have the breakdown region. Okay. So what you see is necessarily we don't generally use or go into the breakdown region, but we have three prominent regions of operations, and that is saturation, active, and cutoff. Okay. Let us talk about active region. In our active region, what do you see? The curves are approximately horizontal, isn't it? There is a small slope here, but it is approximately horizontal. So as I increase VCE, IC does not increase. So IC is dominated or determined only by IB. VCE does not play any part in that. Are you able to understand this?
Yes, sir.
So IB is the one who controls in active region. IB controls IC. Okay, and that relationship is linear because you already know that IC is beta DC into IB. So it is linear relationship. In fact, this is the most important region of the transistor when you are using it as an amplifier, because we want the input signal to be amplified as it is. Amplified in the sense, we are going to see what exactly the amplification means, but the change in the output will be more, and that is governed by your input current. What about saturation? What about saturation? What do you see from in
For a
saturation?
small change in VC, IC increases
IC
rapidly.
increases, that also exponentially.
Yes, sir.
Okay, IC increases exponentially. There is no control of the base current there. Okay.
Yes, sir.
So for small values of VCE, very small values of VCE.
Sorry to say, sir, but screen फिर से freeze हो गई है.
क्या problem है?
सर ये वाला उतने अच्छे से कुछ खास समझ नहीं आ रहा है.
Sorry.
सर ये वाला
क्या?
कुछ खास अच्छे से सर ये वाला समझ नहीं आ रहा कुछ खास अच्छे से.
क्या समझ में नहीं आ रहा? Which part?
वेट सर स्क्रीन दिखने दीजिए.
अभी दिख रहा है?
नो सर.
No, sir.
Is the OneNote page visible?
नो सर.
No, sir. Yes, sir.
अभी दिख रहा है?
Yes, now it is visible.
Get visible. It's showing that I'm able to share it.
Yes, sir, दिख रहा है.
Yeah. Now,
सर दिख रहा है. हाँ सर दिख रहा है.
when this online classes will be converted into offline, really fed up. Okay, what is the part that you don't understand? Didn't understand? Hello? Hello, am I audible?
Yes, sir.
So, which part you didn't understand? Somebody.
Sir, actually अंकित पूछ रहा था वो.
तो वो किधर है? He's not able to respond.
है तो यही.
Is he not able to respond?
Sir, I don't know.
यस सर, सर आई एम देयर।
हाँ, बोलो क्या क्या समझ में नहीं आ रहा है?
सर जैसे आपने सैचुरेशन वाला बता रहे थे ना, जैसे सैचुरेशन रीजन और ऊपर में जो सर जो यहाँ पे ब्रेक डाउन रीजन वगैरह था सर, तो आखिर मतलब ये है क्या, मतलब
रीजन्स, ये रीजन्स क्या होते हैं देख लो पहले। ये क्या होता है कि when you start plotting the characteristics, first of all you will start with here ना, VC 0 से शुरुआत करेंगे। समझो बेस करंट मैंने 120 माइक्रो एम्पियर सेट कर दिया। ऑलराइट, ऑलराइट, अरे भाई रिस्पॉन्ड तो करो।
यस सर।
And if I start plotting the characteristic of the transistor in common emitter configuration, if I start from VCE as 0, तो यहाँ पे IC 0 मिलेगा। मैंने थोड़ा बढ़ाया तो यहाँ पे क्या हो रहा है, ये जो है यहाँ तक तो 0 मिलेगा मुझे, और यहाँ से मुझे तुम्हारा let me show it with a different color। देखो यहां से कलेक्टर करंट बढ़ने लगेगा। So for a small value of VCE, I have IC equal to 0, even if IB is a non-zero value. But after a certain point, after let us say this 0.5 volts, you'll see that the collector current now becomes more or less equal to बीटा टाइम्स द बेस करंट। समझ में आ रहा है क्या? तो ये जो रीजन है जिसमें योर कलेक्टर करंट और बेस करंट के बीच में लीनियर रिलेशनशिप नहीं है, उस रीजन को हम सैचुरेशन रीजन बोलते हैं। समझ में आया अभी? Hello?
Yes, sir.
So always remember that collector current and base current का relationship saturation region में linear नहीं होता है। वो यहाँ पे सिर्फ linear होता है, किस region में? Active region में। ठीक है? So that is how you define the saturation region. ठीक है? अरे yes or no?
Yes sir.
Yes,
so
sir.
cut off region. So cut off region में क्या होता है? When you have base current 0, the base current itself is 0. In that case, even if I increase the value of VCE, your collector current is very, very small. What will be its value? If base current is 0, what will be the value of IC? We already know from this equation.
So 0.
नहीं, 0 नहीं होगा। 0 कैसे होगा? ये होगा ना, ये होगा ना।
Yes sir.
तो ये ICEO है, ये जो है, ये वैल्यू जो है, ये ICEO ही है। उसके नीचे अगर गए, if I like there is no pointing going over there, it says that the transistor is completely off. ICEO का वैल्यू भी बहुत कम होता है। It actually means that the transistor is completely off. Yeah, there will be some current, but we can say that it is very, very less as compared to when we are in the active region. ठीक है?
Yes sir.
In active region itself, continuation में, if I still go on increasing VC to a large value, again यहाँ पे just like common base, you will be having a punch through effect. We have already seen that punch through effect. So after excess VCE, you have the punch through effect. And this punch through effect is causing this very large current increase. ये देखो यहाँ पे हो रहा है ये very large current increase, and this actually may destroy the device. So you should not go into this breakdown region during your operation. ठीक है?
Yes, sir.
Let us see the final curve, that is the transfer curve. Now transfer curve का मतलब क्या होता है? कोई एक इनपुट क्वांटिटी वर्सेस आउटपुट क्वांटिटी. तो यहाँ पे IB वर्सेस IC, इसका अगर मैं प्लॉट करता हूँ तो इट विल लुक again, it will be a linear kind of thing. So if this is your IB in microamperes, and if this is IC in milliamperes, it will be a curve. Linear one at that. Okay. So this is how you define. This is how you get the transfer curve. And obviously the slope क्या होगा इसका?
So beta.
Yes, very good. So slope will be beta DC. ठीक है? So we have now common emitter configuration completed. Now let us go for the last configuration, and that is the common collector configuration. So common collector configuration. As the name suggests, your collector terminal will be common to both input as well as output. Let me pull the figure again from my Visio figures. So this is how the common collector configuration will look like. ठीक से देखो, collector region, this collector, this is base, this is emitter, and this is collector. This is base, this is emitter, and this is collector. You will see that the collector is common to both input as well as the output. ठीक है? तो इसका इनपुट क्या होगा? इनपुट करंट क्या होगा? IB, correct. Actually, the direction will be reverse, but let us keep it that way. IB. और इनपुट वोल्टेज क्या होगा?
So VBC.
ये BBC नहीं होता है. it will still be this. Anyways, I'll just put it in other way so that you will not get confused. So I will draw another figure so that it becomes a little bit easier for you to understand rather than showing it this way. तो ये तुम्हारा हो गया VCC. This is how we will show it. This will be your base current IB. VBE ही होगा input. This will be VCB. And this is where you get the output voltage. Now what is the output current now? It is IE. Okay. This is where you get the output voltage for this configuration. Please remember this carefully. Now even though it may look like this, what is going to be the effective value of input? In the sense, even if I bias it like this, as we say, ये तो IB ठीक है, ये IB ठीक है. What is going to be the effective value of input? मैं ये थोड़े change कर सकता हूँ. If I change VBE, तो ये emitter और base के बीच में input देना जैसे हो गया ना. तो it will be VBC only. Please take it this way. As if I am effectively applying voltage between base and collector in this particular configuration. But it may look like this. Okay? Effectively मैं क्या कर रहा हूं? ये तो constant होगा. तो इसके बीच में, even if I change the voltage over here, effectively what you are doing is you are changing the voltage between this point and this point. It essentially means that it is going to be VCB only. So input current is base current, input voltage is VCB. Please note this. Okay, let us find out the relationship between current and voltages like what we have done earlier. So current relations in common collector configuration, we have IE starting with, again, IE is equal to IB plus IC. That is a starting point. Now we are not interested in IC. We are not interested in IC. Why? Because what is your output current? Output current क्या है? Guys, am I audible?
Yes, sir.
Output current क्या है इसमें?
IE.
Yes, it is IE. Don't worry about the direction flow of current flow. That's fine. So input current is IB, output current is IE. So we are not interested in IC per se. Also we know that IC is alpha times IE plus ICBO. This we have done earlier. Do you remember this?
Yes, sir. Yes, sir.
So then we have IE as IB plus, now I'm going to substitute the value of IC in this, alpha IE plus ICBO. So now if I make this term transpose it to the left hand side. What do I get? 1 minus alpha DC into IE is IB plus ICBO. Okay.
Yes, sir.
So we have IE as 1 by 1 minus alpha DC into IB plus ICBO divided by 1 minus alpha DC. Now you can derive this equation for the relationship between beta DC and alpha DC. We already know that it is 1 minus alpha DC divided by 1 minus alpha DC. And we also know, we have already done this, 1 plus beta DC is equal to 1 divided by 1 minus alpha DC. We have already derived this earlier, right? So I'll substitute, make the substitutions for 1 divided by 1 minus alpha DC. And what do I get? Finally, is IE is equal to 1 plus beta DC into IB plus 1 plus beta DC into ICBO. This is it. Many times we neglect this term. So, neglect the term in the sense we neglect the effect of that term, especially when we are not changing the temperature. So, IE happens to be 1 plus beta DC into IB. Or, what kind of relationship do I get between IE and IB?
Sir, your screen is frozen, sir.
Again,
Yes,
IE by IB.
Yes.
दिख रहा है?
नहीं दिख रहा सर.
Beta DC. Just let me reshare it. क्या प्रॉब्लम हो रहा है मुझे समझ नहीं. Okay, visible now?
Not yet, sir.
Huh? Yes or no?
No, sir.
No, sir.
Okay now?
No, sir. No, sir. Maybe network issue होगा.
Now?
No, sir.
Still not?
No, sir. Yes, sir. Now it is visible.
So which part did you miss?
Sir, वही relationship वो IB और IC.
The entire thing you missed?
No, no, sir. The last part वो linear relationship होगी वो वाला part.
ये इक्वेशन समझ में आया क्या? ये
Yes,
वाला?
sir. आ गया.
It's very straightforward. All right. So we are just going to see very quickly the characteristics of common emitter configuration, common collector configuration, and that is going to be the end of the bipolar junction transistor configurations. So let me quickly do that. So we'll start with A, input characteristics. Now input characteristics will be what versus what? IB versus, yes,
IC, sir.
PCB. मैंने बोला ना पहले से।
Yes, sir.
ये कैरेक्टरिस्टिक्स थोड़े स्ट्रेंज आते हैं। लेट मी शो दोस कैरेक्टरिस्टिक्स। Different, little bit weird characteristics. Because why don't you get similar to common emitter and common base? Why not like that? The reason for that is those were IB versus VBE all the way. This is different. Now what we have is IB versus VBC. Please mute yourselves. So these are the characteristics that you get. And why do we get this? Because we have VCC is equal to VCB minus VBE. So these are indirect characteristics, or simply VCB as VCE plus, sorry, it should be VCE plus VB. देखो यहाँ पे this is your VCE or VEC, doesn't matter, and this is VCB and this is VBE. Rather, this is VBE and this is VBC. So VCE is addition of VCB, VCE, VBE. This is addition of VBE and VBC. That is how you get this VCB. So when collector based junction is reverse biased and emitter based junction is forward biased, VBE remains around 0.7 volts for silicon. That is what we can say from here. Okay. Let us go for quickly with the output characteristics. Yeah, are the characteristics visible to you?
Yes, sir.
Okay, again we see the three regions.
Yes, sir.
But now output current is emitter current and input current is base current. So it's very similar to common emitter characteristics. Very similar. Okay, that is the reason why I'm not going into more details. Observations are exactly the same. And finally, the transfer characteristics. What is the relationship between output current and input current that you get? This one. No? So what do you expect? Transfer characteristics, what do you expect? Between it will be between IB and IB versus what?
Sir, IE.
Correct. So again, you expect a linear relationship.
Yes, sir.
I draw it here. This will be IB in microamperes. This will be IE in milliamperes. You may get curve like this one. Okay. Now, why doesn't it start from 0? Similar case with the previous
Sir,
one.
because of ICE.
Because of that saturation. यहाँ पे saturation जो है ना, तो 0 के आसपास वो नहीं होता. ठीक है. So, and what is the slope again?
Sir, beta.
1 plus beta DC. Remember. यहाँ से ना. This is what we have done. See?
Yes, sir.
Right. So we'll stop here. There is one comparison table which I wanted to give you, but we don't have time for that. We'll start with a new unit from the next lecture. There are a couple of things which are still left, like the Schottky diode, Zener diode, is what is left. We'll do that later on. Okay, at the last.
Yes, sir.
Fine. So I'll stop here.
Thank you, sir.